By the end of this lesson, the students will be able to state Lee-Chatelier's principle, identify the factors affecting chemical equilibrium, understand the effect of change in concentration on equilibrium in terms of Lee-Chatelier's principle, explain that Kc is independent of the change in concentration. The word equilibrium basically refers to what is called a balance of forces. Let us look at this balance of forces in a weighing scale. Click on the screw to lift the empty pans up. Click the sugar button. Now click the wooden block button. The weight of the sugar is now balanced by the weight of the wooden blocks. The scale is said to be in a state of mechanical equilibrium. Click the wooden block button. The equilibrium state has now been disturbed. The equilibrium state can be re-established by adding more sugar. Click the sugar button and note what happens. A chemical equilibrium is also a state of balance. It is a balance between the forward and reverse reactions. Changes in concentration, temperature, or pressure may disturb the equilibrium. When this happens, the equilibrium will then shift until a new state of balance is attained. A new state of equilibrium can be attained by an increase in the rate of the forward reaction so that more of the product is formed. The equilibrium is said to have shifted to the right. A new state of equilibrium can also be attained by shifting the equilibrium to the left. The rate of the reverse reaction is increased and less of the product is formed. If a system at dynamic equilibrium is disturbed, the system will change in the direction which tends to reduce the disturbance, whereby the equilibrium is restored. Click the Lee-Chatelier's principle button. Summary: a chemical equilibrium is also a state of balance between the forward and reverse reactions. Changes in the conditions of the system such as concentration, temperature, and pressure may disturb a chemical equilibrium. If a system at dynamic equilibrium is disturbed, the system will change in the direction which tends to reduce the disturbance, whereby the equilibrium is restored. A state of chemical equilibrium is said to have been reached when the concentrations of the reactants and products remain constant over time. Consider the case of the gaseous reaction of hydrogen with iodine. The Kc value of the equilibrium system established at 440 degrees Celsius is 49.5. We can determine whether a mixture of iodine, hydrogen, and hydrogen iodide has reached a state of equilibrium by substituting the concentrations of the reactants and products into the fraction given above. The value obtained is called the reaction quotient, Q. For a reaction mixture to be in a state of equilibrium, the reaction quotient must be equal to the equilibrium constant Kc. Click the Mixture A button to calculate its reaction quotient. Mixture A is in a state of chemical equilibrium as its reaction quotient is equal to the equilibrium constant. Let us look at the equilibrium between two ions of copper. Tetra-aquo-copper 2 plus ion is blue and tetrachlorocopper 2 minus is yellow. An equilibrium mixture of the two is blue-green in color. Click the NaCl button to add Cl- ions to the equilibrium mixture. What do you observe? Answer: the mixture immediately turns from blue-green to yellow, but eventually turns back to green as equilibrium is restored. Addition of Cl- ions changes the concentration of this reactant in the mixture. The value of the reaction quotient is now no longer equal to Kc. The equilibrium is disturbed. The addition of Cl- ions is the disturbance applied to the equilibrium. To offset this disturbance, some tetra-aqua-copper 2+ react with the added Cl- ions and the equilibrium shifts from left to right. There is now more tetrachlorocopper 2- ion and uncombined H2O. A new position of equilibrium is reached once the reaction quotient becomes equal to Kc again. Is the composition of the equilibrium mixture the same as before? Answer: no. We can also change the position of equilibrium by removing a reactant. Click the AgNO3 button to add NO3 ions to the equilibrium mixture. Take note of the color change. The added Ag+ reacts with Cl- to form insoluble AgCl. The removal of Cl- ions is the disturbance affecting the equilibrium. Why does the color turn to a darker blue? Answer: the equilibrium shifts from right to left to form more Cl- ions to replace those that have been removed. More of blue tetra-aqua-copper 2+ ion is also produced. Let us take a look at another equilibrium system. The color of the solution in this system is due to the red FeSCN2+ ion and the yellow Fe3+ species. Click the FeNO3 thrice button. The red color of the solution deepens. The dissociation of FeNO3 thrice in the solution results in an increase in the concentration of Fe3+. Click on the appropriate arrow to re-establish equilibrium in the system. Click the ethane dioic acid button. Ethane dioic acid ionizes in water to form the oxalate ion C2O4 2-, which reacts with the Fe3+ ions. Click on the appropriate arrow to re-establish equilibrium. Summary: when a reactant or product is added, the system will shift in the direction that will partially consume the reactant or product to restore the equilibrium. When a reactant or product is removed, the system will shift in the direction that will partially replace the product or reactant to restore the equilibrium.